2023. And as you can see, already on Santanu Mukherjee and Takaaki the website. I mean, any questions? We're using the hashtag introduced portfolio to and medical content. Thieme chemistry products, you may know, are science of pharmaceutical substances, and then the journals SYNTHESIS, SYNLETT, SYNFACTS, SYNORM, and SYNOPEN. I would also like to mention that we have launched a new journal that aims to tackle challenges. It's called Sustainability and Circularity Now, and it focuses on the discovery, materials, and synthetic procedures. The journal is open for submissions, so and APC here. I would like to introduce SYNTHESIS, this paper journal, and we publish 24 issues per year. It provides dependable research results and full characterization of all important new products. And we also publish primary data. Editorial board members, shown here, take care of the reviewing process. I also and letter journal, and it published research results and current trends in chemistry. Synthesis. Speed is of importance. So we offer select review, normal peer review, and this speeds up the review. We are also for new, highly motivated crowd members. So if you are interested, please contact us. We're publishing special issues in our journals. Publishing, so for example, in SYNTHESIS, we have dual catalysis upcoming. In SYNTHESIS on isotopic labeling, the synthesis of alkyl. In SYNOPEN, we focus on polymer chemistry and heterocyclic chemistry. We have cellular matrices. So if you want to learn more, please visit the journal with all. So I would just, the next one will be on and we have invited again to speakers. Also, we have done already in the past. To your experts interested, please visit the Cassini website. Today's webinar, so as I said, we have two fantastic speakers: reaction development and application in Japan on total SYNLETT. Also, let you know, and so this honors best original research. Nominated three papers. Per decision. January. Science in college in and his man he was working with Professor Stark with Stark with Professor at Harvard, Professor at the Indian Sun. He is Professor 11 Academy for the year 2019. He also received several more awards. A fellow of the Royal Society of Chemistry. He is also an associate editor of Organic and served as a member of the editorial advisory board of the Journal of Organic Chemistry. And in 2023, he has received the SYNLETT Best Paper Award. And he's all report. So, Santanu, I would like to welcome you. And yes.
Thank you, Steffi, for very generous introduction. For sharing. My screen is visible?
Yes.
For very generous introduction and for the opportunity to present as a part of the presentation today. But I have been involved in more than a decade in our lab. So our group is primarily already showed here, mostly homologous reactivity, electrophilic halogen-induced reactions, getting drawn towards transition multicatalysis. With the whole, more specifically to combine our group primarily focuses on reactants and requires a lot of screening. Once we are down on there was a lot of unexpected findings. Up with the mechanism and in the overall process. Has been our past since we start a journey in the concept of selecting what of the type so-called then are actually so-called enhanced topic. We have prochiral center. You can convert both. Is possible. Convert either of them probably with an equal ratio, and that will lead to a mixture of two enantiomers. And if you convert both, that will bring back do this transformation selectively. Even with the meso compound, the same thing is possible, and that can be multiple stereocenters in a single state. So this type of reactions are commonly known as enantio group differentiating reactions. Now, there are these questions, and even most importantly, why even bothering about breaking symmetry. Now, before we go to today's exact topic, let me just give you an example of what I just presented you in the form of a cartoon molecule. You can imagine this is something very similar to that. We have this nitromethyl group, 2-nitromethyl group, and this center is a prochiral center. Now, we can convert one of these 2-nitromethyl group into something else, and that can be done in two different ways. Either we can do a stereoselective or an enantioselective modification of one of the nitro groups, or we can do something at this methylene group here. So we chose to do the latter one, and with the help of this bifunctional tertiary thiourea. And so how does it work? So we call it an ideal desymmetrization because we retain all the functional group that are present in the starting material, but still be able to break the symmetry present in the starting material. Now, the way what we thought initially the reaction is proceeding via is an enantio position selective conjugate addition of the nitronate through this type of a dual activation of both the substrate using tertiary aminothiourea catalyst. And once the Michael addition takes place, this proton becomes acidic, so it can eliminate nitro group in the form of a nitrous acid, and then followed by isomerization of the exocyclic double bond to the final product. So that was the initial hypothesis. And based on that, we went ahead and tried the reaction on, or tested the reaction on some of the other class of compound like meso quinones of this type. And in this case, also, we can get the product with very high enantiomer selectivity using a similar type of catalyst. And in this case, again, this is our mechanistic hypothesis that we had at the beginning. And in this case, we can provide some evidence in support of this mechanism for one particular substrate, apart or along with the final CH alkylation product or the CH methylation product. We could also isolate the intermediate Michael adduct, that is this one. And we can isolate, purify, characterize completely. And once we treat this with an achiral base, it goes to the final CH methylation product with the same level of selectivity and with the same sense of induction. So that shows that this is indeed the pathway that is operating. The initial enantiomer determining step is the enantiomer position selective conjugate addition. Unfortunately, in the case of cyclopentene dione, we could never detect or isolate anything that is closely related to this Michael added. So that brings us the question, like, what is the actual mechanism? Is it the same mechanism as the cyclohexene dione that is followed in this case, or something else is happening? More specifically, what would be the rate and enantiomer selectivity determining step in this particular case? And also, we also wanted to know how does catalyst control the remote stereo induction, that is 2 bonds away from the reaction site. To understand these doubts, we thought of combining an experimental technique that was popularized by Dan Singleton. This is called natural abundance 13C kinetic isotope effect with the DFT calculations. And we did that in collaboration with Professor Jennifer Hirsch's lab in Binghamton University. I will not take you through the entire study. What I'm going to tell you in this case is that, unlike in the case of cyclohexene dione, where the enantiomer position selective Michael addition is the enantiomer determining step, in this case, it is the nitrous acid elimination that turned out to be the rate and enantiomer determining step of this process, which was quite surprising to us at the beginning. We also tried to look at the origin of enantiomer selectivity, that how does catalyst control the selectivity that is 2 bonds away from the reaction site. So these are the 2 competing diastereometric transition state. The major one that is giving the R product, this is the transition state leading to the R product, and this is the minor one. So what you can see, one of the factors, this is not the only factor, but one of the factors responsible was an favorable CH-F hydrogen bonding interaction. And that leads to somewhat stability to the major transition state. And to provide, again, some experimental evidence, we prepared a catalyst where we replaced the CF3 groups in the catalyst with the dimethyl group, and this catalyst B turned out to be less enantiomer selective, although it is significantly still enantiomer selective compared to the previous catalyst. And that of course also corroborates well with the predicted enantiomer selectivity that we have seen in this case. Now, in this whole process, what we learned was that nitro can actually act as a good living group. So we are thinking of whether we can actually translate this knowledge to some other transformation that I have showed at the beginning. And we could do that. We have developed this so-called umpolung alpha alkynylation of a beta keto ester. So this is the product. If we start from the product and do a retrosynthetic analysis, that leads to these 2 starting materials. Unfortunately, both of them have the identical polarity, that is both a nucleophilic and the alpha position. So therefore, they cannot be combined to form a CC bond. However, if you put a nitro group at the beta position of the enone, we can convert this nucleophilic alpha position to the electrophilic position. So therefore, the addition can take place, and then followed by, at the end, elimination of the nitro group can give rise to the desired product. So in this process, nitro controls the multiple steps in this overall process. Now, in this, again, our working philosophy, we have shown that the scope, mechanistic understanding, and the knowledge generated led to the discovery of a new reaction. But while thinking of the application of this process, we are actually drawn to this interesting class of molecules called ladderin phospholipids. Now, these molecules were first isolated in 2002 from a bacteria called anaerobic ammonium oxidation bacteria, which essentially converts ammonium nitrite to molecular nitrogen in the ocean. And this reaction happens in a compartment inside the enzyme cell that is called anamoxosome. And in this process, actually, hydrazine is a byproduct in this process, or an intermediate in this process. And as we know, hydrogen is toxic to the cell. So therefore, it was thought that this membrane actually prevents the leaching of the hydrazine across the membrane. And that's where this lipid, from where these ladderin phospholipids were isolated, that's the main role of that. However, if you look at the other part of the cell, you can see there is a pH difference across the membrane. Inside anamoxosome, it is 6.3, outside it is 7.3. So in 2018, Stephen Boxer and Noah Burns group in Stanford actually did a thorough investigation, and they showed that this membrane does not stop the permeation of hydrogen, it actually stops the permeation of proton across the membrane. And this pH gradient leads to the proton motive force, which is responsible for the ATP synthesis in this cell. Now, as I mentioned, this from this lipid bilayer, this adenine phospholipids were isolated. And these are some of the examples called 5,3-phosphatidylcholine and 3,3-phosphatidylcholine. Then 5 and 3, this basically denotes the number of concatenated cyclobutane that are present. That is 3 in the case of 3-ladarinol and 5 in the case of ladderenoic acid. Now, there has been quite a few synthetic routes to these compounds. I will not take you through all of them individually, but I'll just tell you quickly how a couple of synthetic routes to the 3-laderinol. The first one was reported by Burns group in 2016. So they rely on an enzymatic kinetic resolution at the beginning of this dibromodiol to break the symmetry of this. And then after oxidation to the corresponding indione, they did a 2+2 cycloaddition to form this core structure. Afterwards, they can actually do the coupling with a long chain alkyl zinc to eventually lead to the 3-laderinol. Kevin Brown approach was quite different. They actually did an organocatalytic isomerization reaction to form a chiral alene, which then participates in a chirality transfer 2+2 cycloaddition reaction to form this bicyclic compound. And they again coupled it with a very similar alkyl zinc species to get this product, and that was converted over several steps to the final 3-laderinol. So one common feature between these two synthetic routes is that the stereocenters are actually established at the very early stage of the synthesis. So what we thought that whether it is 5-ladderenoic acid or 3-laderinol, if we can break this CC bond, we can actually introduce the alkyl chain at a very late stage of the synthesis and break the symmetry of these meso compounds, and we can form the structure. That means the stereocenter will be introduced at a very late stage of the synthesis. And as a result, we will be able to make the synthesis quite modular for preparation of many other analogs that could be useful to answer some of the questions. Now let's focus on the 3-laderinol to begin with. And the transformation we are talking about is a cross dehydrogenative coupling between two sp3 centers. This is an extremely challenging transformation, particularly if you need to consider the chemo, regio, diastereo, and enhancer selectivity. So we thought of making the process somewhat simpler by adding some functional group to these molecules, that is converting the simple cycloalkane to the indione motif. Now, if you can cleave this bond, that leads us to these two fragments, and we were confident that we would be able to stitch them together using the CsP2H alkylation reaction that I just mentioned, using nitroalkane as the alkyl source in this process. Now, there has been two different problems that we identified, or the possible problems that we identified at the beginning in the drawing board. One of them was that the first step of the reaction in the case of cyclohexene enhancer position select and the substrates, the substituent that are present here required actually, unlike in the case of trans-cyclobutane fused cyclohexene dione, which are present in this ladderenic motif. So where this H are actually somewhat close, even still quite far from each other. So we are not sure whether we will be able to discriminate the two enantiomer positions of this type of molecules. Second thing is we need to have a practical synthesis of this meso precursor to our target. Now, to tackle the second problem rather, so we thought, can we have a simplified model substrate just to check whether we can actually discriminate between the two enantiomer positions in the substrate. And we particularly chose the cyclopropane fused cyclohexene dione because they are very easy to synthesize compared to the cyclobutanes. And if we look at now the desymmetrization of some of the so-called 4,1,0 bicycloheptanes, and most of the reports rely on the opening of the cyclopropane ring, which is not surprising because it's a very strange system. And the first report was known about 30 years ago, where they use a cobalamin as a catalyst to do the isomerization of cyclopropane, and that proceeds through this type of a pathway, and they get they can obtain decent enhancer selectivity. There was another report by Mueller group where they can simply open the cyclopropane through an SN2 type reaction using thiol as a nucleophile, using Bronsted basic synchron alkaloids. There was a series of reports starting with Gilmore and then a few other groups where they can use a secondary amine catalyzed cascade reaction, first with an nucleophilic chlorine and then with an electrophilic chlorine, and then that they can also get this. But again, as I mentioned, that in all these cases, the reaction proceeds through the ring opening of cyclopropanes. We were interested in the ring retentive desamination following with the CH alkylation reaction, following the same mechanism that I mentioned previously, that enhances position selective conjugate addition, elimination, and isomerization. I'm not going to the entire optimization process, but my student Sayan spent a lot of time on this model substrate, so-called model substrate, and he could eventually come up with this tertiary amino squaramide catalyst to desametrize this type of fused cyclopropane fused cyclohexene dions with moderate to high yield and moderate to good level of enhancer selectivity. These are generally higher if we put a 2-methyl group, which is not surprising because it is enhancing the steric bulk at that position, and that actually gave the product with high enhancer selectivity. Now, this type of 6-3 fused systems are present in many natural products, particularly this type of carrying natural products. And so we thought of synthesizing, and this looks very similar to one of our products. So we thought of doing an enhancer selective synthesis of this one. So in this process, we need to first prepare the substrate. We did it from this endo-novoninoquidone through a cyclopropanation. Retro Dielsalder gave us the starting material, the meso compound, which we subjected to the desametrization reaction under our condition, and that gave the product with very high enhancer selectivity. Now, traditionally, this type of natural product that's carrying dions were generally obtained through oxidation of 3 carines. That was the chiral pool approach. And we developed the first catalytic asymmetric synthesis of this process in the form of a model substrate to our laddening phospholipids. And we are thankful to Thieme for selecting or recognizing our work with the SYNLETT Best Paper Award of 2023. Now, having done that, we could have enough confidence that we will be able to desametrize the cyclobutane fused cyclohexene as well. Now, the question is, how do we prepare this one? Now, there has been quite a few methods for the synthesis of ladderings, but some of the systematic ones came much later. The initial reports by Mindworld appeared again like almost 50 years ago, and they used a 4+2 cycloaddition of this anti-aromatic cyclobutadiene to form these pterodactyl dienes named after these flying dinosaurs. There were some modifications of this method by Professor Mehta's group, where they can form up to 13 ladderings. But the exciting part from our side was encountered with Martin's report in 1981, where they used a Rambach-Backlund reaction for forming the cyclobutene scaffold. So we thought of using this method. So for this purpose, the first reaction we had to do was a 2+2 cycloaddition between malic anhydride and ethylene, and that was our reaction setup where Sion did that, and that was helped by Professor N.D. Pradeep Singh from IIT Kharagpur for helping us building this setup. Now, this compound can easily be converted to the corresponding diol, and in case your funds approves, you can actually go ahead and buy this dicarboxylic acid, but it's quite expensive. So we thought of starting with an ethylene and malic anhydride. Both of them are fairly cheap. And then once we have the diol, we can actually convert it to this bicyclic compound to the dimesylate by displacement reaction. Now, if we oxidize, we can get to the corresponding sulfoxide. We can do an alpha chlorination of the sulfoxide. This is again something unusual for a Rambach-Backlund reaction because that's normally done with sulfones. So in this case, it was showed by Noah Burns' group that this works better. So then in this process, we can actually get this bicyclohexene or the 2 laddering scaffold. Now, having accessed that, we did a 2+2 cycloaddition followed by oxidation to get our meso substrate. Then we did our key reaction, that is sp2 CH alkylation reaction or the desametrizing CH alkylation reaction to get the product in 69% yield and 90-10 ER. We need to remove the functional group that we have introduced at the beginning. And for that, we initially converted this dione to the corresponding diene under a copper catalyzed transformation. And hydrogenation under trapped risk catalyst gave the correct diastereomer with a TBS protected alcohol here, which we can clip with a 1 normal HCl to give us +3 ladderenol. And we can get an extra structure. This is the natural product. We can convert it to the corresponding carbamate, and then you can go and get an extra structure of this compound with improved enhancer selectivity, and that also establishes the absolute configuration of this compound further. And as I mentioned earlier, so our synthetic route relies on the late-stage enhancer induction, and that leads to the synthesis of some of the model compound as well, that I will not go to that. All right, so having synthesized enhancer selective synthesis of, or completed enhancer selective synthesis of +3 ladderenol, we thought of going for the 5-ladderenoic acid. Now, as I mentioned, there has been quite a few reports, primarily by these 3 groups, or mostly by the 3 groups. So the question is, why do you want to synthesize 5-ladderenoic acid? Now, if we look at the core structure of both these compounds, and when all the dotted bonds are actually intact, we have 5-ladderenoic acid. If we break this red bond, we get 3-ladderenol. And systematically, if you break one by one, we can get 4 different structures. Out of these, 3-ladderenol and 5-ladderenoic acid has been isolated as natural product. But what about the other 3? We asked this question that, can they also be natural product that has not been isolated yet? Or maybe nature chose not to make them, or made them but discarded them through the evolution process because they were not properly serving their purpose in providing membrane impermeability. So we thought there is only one way to find out is that if you can make all of them and test their properties as a phospholipid in the form of membrane permeability. More specifically, we need to come up with a unified strategy to make all of them. We have already made 3-ladderenol, so we just need to make 5-ladderenoic acid and 3 of its so-called analogs. Now, there is a common feature in all these cases. The long chain is now attached to the cyclobutane ring. Unlike in the other case, in the case of ladderenol, where the long chain was attached to the 6-member ring, therefore, we could use this desymmetrization of this meso-indione for synthesizing 3-ladderenol. Now, having a cyclobutane ring here, this direct desymmetrization is not possible because we cannot have a 4-membered indione motif. So we thought if we can introduce a 6-membered ring here with the proper functionality, we might be able to clip this bond in the same way that we have done in the case of 3-ladderenol. Only what we need to do at this step is remove the 6-membered ring that was introduced at the beginning. So overall, we need a deconstructive strategy. Now, this is something I'm going to explain to you using this cartoon representation once again, or the truncated fragment. But this is going to be our common structure for all those 4 compounds. That is 5-ladderenoic acid and 3 other analogs of that. What our initial idea was to have either a 2-carbon deletion to get this dione, and that can be deoxygenated to get the final compound. Or we can have a 3-carbon deletion approach to get a ketone. Again, a deoxygenation will lead to the final compound. There is another possibility of a 1-carbon deletion here and followed by deoxygenation and hydrogenation. But these 2 compounds are enantiomeric, so therefore we need to modify the catalytic methods accordingly. And depending on whether we choose to have a 1, 2, or 3-carbon deletion, we need to vary the chain length of this long chain nitroalkane accordingly. So I'll take you through the entire process, which we have divided into 3 main steps. One is, of course, the starting preparation. Second is the enhancer selective desymmetrization reactions, which we know would work with banking on our previous experience. So initially, we focused on the deconstructive carbon deletion approach, using a model substrate, which can be easily prepared either as a methyl form or as the long chain one. So our initial idea was to do an ozonolytic cleavage of the CC bond to get this alpha ketoaldehyde and 1,2-diketone. And we thought we should be able to do a 3-carbon deletion here using a Wilkinson catalyst to the decarbonylation. In reality, when we actually did the ozonolysis in DCM, we got this very complex star molecule, which is nothing but a cyclic analog of this compound. So we thought if this is an equilibrium, we might be able to do the decarbonylation. But it actually looks like we can't because this is a very stable compound. If we do the ozonolysis under somewhat different condition, under oxidative condition, we can remove one of the carbon directly at this step. Now we have the carboxylic acid. We thought, can we do a decarboxylation reaction? But we instead got a cyclized compound. So we tried many other things. I will not take you through the entire process, but all these attempts of 2 and 3 carbon deletion approach actually failed. So we had to come back to this 1 carbon deletion approach. Again, this would convert 3 different steps. One is the chemoselective deoxygenation of these 2 carbonyls, followed by the cleavage of the CC bond, and then followed by the 1 carbon deletion. So this is the 3-step deconstruction approach that we had to use. So we thought of focusing initially on the chemoselective deoxygenation, and this can be done fairly easily under the Leuchter reduction at the beginning, which gave a single diastereomer. If we treat this compound with BF3 etherate, we actually get this deconjugated eno through possibly a final Lagrange pinnacle rearrangement, where the BF3 coordinates to the less hindered hydroxy group, and then hydride transfer, and then elimination takes place. Of course, we have the double bond in the wrong position, but we could actually get the conjugated one for the longer time. And in this case, the OH falls off, but that's not a problem. We can actually do the chemoselective deoxygenation reaction. Now, coming to the CC bond cleavage, that can be done easily. We can do the hydrogenation, production of the alcohol, reduction of the ketone to the corresponding alcohol, and followed by elimination by methylation. And that gives us the CC double bond. Now we can cleave this with ozonolysis to get the ketoaldehyde. Now what left is a 1 carbon deletion. Once again, decarbonylation failed, but we can do a decarboxylation reaction with the Barton type decarboxylation, and that gives us this keto compound. Now we can remove the oxygen through the deoxygenation reaction under Wolff-Kishner condition, and that gave us the final product which we are hoping to get. So starting from our desymmetrized compound, in overall 11 steps, we can get 11% overall yield of this model substrate. Now, having done the deconstruction, we needed a method for preparation of this 4th laddering. So this is something I have already talked about, and these 2 double bonds, 2 cyclobutanes are already there. We can force the 3rd cyclobutane by a 2+2 cycloaddition with cyclopentanone, and through the alpha diazoketone, Wolff rearrangement gave us the 4th cyclobutane ring, and then we did a decarboxylative bromination followed by elimination to get the 4-laddering motif. Now, with the 4-laddering in hand, we can do the 2+2 cycloaddition followed by oxidation to get us our desired miso compound. So starting from ethylene and maleic anhydride, this overall post-process takes 14 steps and 6 chromatographic purification. Now, having accessed all this, achieved all the individual steps, now we came to the key step of the synthesis, that is the enantioselective CH alkylative desymmetrization step. Using our method, now we can prepare this in very high yield, about 72% yield and decent enantioselectivity. Now the end game, as I already told about the deconstructive 1 carbon deletion approach to get 5-ladderenol, which can be oxidized to the corresponding ladderenic acid in 82% yield and about 78% EE. And the overall process takes about 11 steps in 6.4% overall yield with only 4 chromatographic purification. And so optical rotation as well as the proton and 13C NMR matched quite well with the literature reported ladderenic acid. And so now we not only have a unified strategy for making all of them, we have synthesized 5-ladderenic acid and inverse 3-ladderenol, one of the 3 so-called unnatural molecules. So we are currently working on synthesizing the 2 other unnatural analogs of 5-ladderenic acid. So today I told you, I discussed basically the application, primarily the application of our alkylative desymmetrization reaction for the synthesis of 3-ladderenol, 5-ladderenic acid, and other unnatural analogs. Of course, I have not done any of this work myself, but I hope I could able to give some of the answer to some of the questions that I asked at the beginning of this presentation. So my big thank goes to my student, my single-man army, Sion Ray, who almost single-handedly completed the synthesis of both these molecules. Of course, he was helped by Subhajit in the early phase of the 3-ladder synthesis in the form of the substrate scope. Prof is currently working on the synthesis of some of the other two unnatural analogs. And the initial CH alkylation reactions was developed by my first student, Dr. Madhusudan Manna, and subsequently by Rahul Sarkar. Deepak Behra, who is currently a grad student, he worked for a short time in our lab, and he is currently, he helped us with some of the starting preparation of the 5-ladder acid. This is my present group. I must thank the funding agencies for supporting our research over the years, and my collaborators, Jennifer and my colleague Garima. They help us understand the mechanism of some of the reactions that we develop. We are currently doing a collaboration with Pradeep Tarabdar, who is helping us to understand the membrane permeability study of the permeability properties of some of these molecules that we are making. Last but not the least, I must thank Thieme and the SYNLETT editorial board for honoring our work with the Best Paper Award. Let me also take this opportunity to congratulate Professor Takaaki Sato and his team for this beautiful work, which was recognized with the Synthesis Best Paper Award of last year. And I would like to thank you all for your attention, and I'll be happy to answer any questions that any audience may have. Thank you so much.
Thank you, Santanu, for your fantastic talk. I think it was a pleasure to listen to your experiments, to your results. And yeah, there are questions. There's also the chance to ask further questions. We have received 3 questions for you for the moment. So we start with the first one. The first one is, what is the synthetic utility of the enantioselective alkylation desymmetrization? May you provide us examples from total synthesis where this method was used?
I believe this question was asked while I was still talking about the reaction and the mechanism, and before I actually came to the application of this reaction for the synthesis of 3-ladder enol and 5-ladder enoic acid. I believe I was able to answer the question already.
Yeah. I agree. But if the person who asked the question still has another question or a following question, so yeah, please feel free. But I agree. I think you explained it already. So let's move on to the second one. It's related to the catalysts. So in many cases, thioureas are effective over urea catalysts. Can you please comment on this? And the second, which is related, is the square amide catalyst an efficient catalyst in your desymmetrization process, also over thiourea catalysts? And could you please comment on this?
Yeah, this is a good question. So ureas and thioureas, they are almost, looks like identical, but they have some intrinsic properties that sets them apart. Ureas tend to aggregate in the organic solvent to the intramolecular hydrogen bonding, or actually intermolecular hydrogen bonding. They assemble. Thioureas tend to stay in the monomeric form. Of course, there are differences in NH acidities. Thioureas are more acidic compared to the urea. But when it comes to a particular reaction, we need to normally try urea, thiourea, and square amide. Although at the beginning of the discovery, it was thought to be specific for nitroalkanes or nitro group, but later on it was found to be coordinating with a varieties of organic functional groups. And depending on the reaction or the reaction partners, in some cases, one works better compared to the other one. So when I say works better, it actually gives better enantiomer selectivity. But if a particular reaction is catalyzed by urea, thiourea, and square amides are also likely to catalyze the same reaction. Now, in terms of enantiomer selectivity, there is some difference, but most of the time difference is not tremendous. They're typically 5 to 10% EE difference, some cases even small, even less. Full details of how it works exactly, why one gives higher enantiomer selectivity could be related to the acidity of the NH protons, and that can give to a much more tighter transition state. But it again varies from a particular reaction to reaction. The same is also true for square amide catalysts. I hope I was able to answer the question.
Yes, thank you. So the final question I have for the moment is, conjugate additions of nitroalkanes are common organocatalytic reactions but it's not that common to see the kind of loss of NO2 that you observed, resulting effectively in a direct alkylation of the electrophile. What do you think determines whether NO2 is lost or whether it stays on in the formation of the Michael adduct?
Very nice question. So if you look at some of our product, let me see if I can actually go to some of the reactions, right? Yeah, we can go to this one. So if you think of it as simply in-on motif, then the Michael addition will give rise to this product. But now in our case, it is in-dione. So therefore, the proton, one of the proton that is bitter to the nitro is also alpha to a carbonyl group that makes it quite acidic. So this is actually the key for the elimination process. If you have a simple alpha beta unsaturated ketone or aldehyde or ester or amide, then this proton will not be sufficiently acidic. So therefore, the elimination of the nitrous acid will not take place. Only because it is in-dione, the reaction, the elimination takes place.
And there's a follow-up question. Apart from NO2, were you able to use any other leaving group?
We tried a few other like sulfone and others, but none of them are as effective as the nitro group. It's not about the leaving group ability of that. For example, you may think cyanide is a good leaving group, but the corresponding alkyl nitriles are significantly less acidic compared to the nitroalkane. So therefore, removal of the alpha proton also has to be done in a milder condition. So nitro actually is a good balance, which confers a higher acidity to its alpha proton and also acts as a good leaving group. Cyanide can be a good leaving group, but alpha proton is much less acidic. So therefore, it would require a much stronger base for elimination. There can be other possibilities like sulfonates and so on. But again, I mean, the preparation and stability of some of this compound may not be as good as nitroalkanes. Nitroalkanes are actually very stable compounds. Many of them are commercially available, particularly nitromethane and nitroethane. So we felt that this is probably the best choice that is available with us at the moment.
Okay, thank you very much for answering. There's another one. What happens if the nitroalkane has two substituents?
Yes, it depends on the substituents. Again, this is related to the acidity of the proton. If the substituents are going to reduce the acidity, of course, it's going to make the center much more sterically hindered. So if the substituents are bulkier and it makes the proton less acidic, then there will be no reaction. And of course, the steric bulk also plays a role. So we tried isopropyl, for example, that did not give any product, but we can have some of the electron withdrawing groups in those cases, and that can actually give rise to the product. So that we have noticed it. Yeah, so that's basically the answer to the question. That.
Okay, so thank you very much for answering these questions and for your fantastic talk. It was really a pleasure to listen to it. Also, the feedback in the chat is quite good, so amazing results. Yeah, so I want to just take over again. I will share my screen again. And we will continue with our second speaker. But before we move on, I would just to mention again, or we had, my colleague has also posted the link to the paper from Professor Mukherjee. And I also want to finish this presentation with a quote from Benjamin List, who was our former editor-in-chief. And he's saying that Mukherjee and his team described an extremely elegant and highly enantioselective approach to desymmetrize B-cycloheptenes. Their organocatalytic reaction features the use of nitroalkanes as source of alkyl groups in a CH alkylation. The method is applied in the first enantioselective synthesis of 3-carene dione. So thank you again very much for this fantastic talk. And now we will continue with our second speaker, which is Professor Takaaki Sato from Keio University in Japan. He received his Bachelor of Science degree in 2001 from Tohoku University and his PhD degree with Professor Masahiro Hirami also from the same university. He spent then 2 years in Professor Overman's group at the University of California, Irvine, as a JSPS fellow. And he then joined the Department of Applied Chemistry in Keio University as an assistant professor in 2008. He was promoted to associate professor in 2016, and in 2022 he started his independent career in Keio University. Also, Professor Sato has received several awards. So he was awarded the Otsuka Pharmaceutical Award in Synthetic Organic Chemistry in 2008, the Young Scientists Research Award in Natural Product Chemistry in 2014, the Incentive Award in Synthetic Organic Chemistry from also Japan in 2016, and the Thieme Chemistry Journal Award also in 2019. In 2023, he has received the SYNTHESIS Best Paper Award, and he now will present his work in this talk. There will be also in the chat window the link to his paper, so you can access this for free. And Mark Lautens, the editor-in-chief of SYNTHESIS, stated that Professor Sato and his team described a detailed synthetic study of the stereoamide class of heterocycles, including tricyclic, tetracyclic, and pentacyclic frameworks. The paper includes a stereodivergent strategy in the creation of a fully substituted butenolide, a comprehensive investigation that outlines several optimization reactions, careful structure elucidation and discussion, and anti-inflammatory assays are highlights of this exciting study. So please share your work now. I will unshare my screen, and you can take over now. So you are stood, so we cannot hear you yet. No, looks good. Yes, the slides are visible. Perfect.
Okay. So, thank you very much, Dr. Baumann, for kind introduction. And it's very honor for me to be selected as the Best Synthesis Best Paper Award in 2023. And I'm grateful to the Thieme Chemistry and editorial boards of the SYNTHESIS and SYNLETT. Also, I'd like to thank all organizers for giving me a very nice opportunity to talk here. So today, I'd like to share with you our long story of the total synthesis and anti-inflammatory activity of stem So here oxidation could be possible. So usually complex mixture, but manganese dioxide provided no product. But still the epimerization was a problem. And even if you succeeded to oxidize in a flask, isolation was also a problem. So if you use a silica gel, the epimerization happened through the silica gel. So it was difficult. It was very challenging to oxidize and isolation.
Yeah, I can imagine. Yes. Okay. Yeah, there's another question. How is about the characterization technique of the betanolide isomers? So
that's a question. Yes. So tetrasubstitutolefin is not easy to determine the stereochemistry. And we use kind of empirical. We use the NOE and also empirical results. So that means that we can see the NOE. So stereochemical determination was possible. So when the butanolide has a Z conformation, usually higher field of the carbons, and the E conformation has a lower field. So we usually, if you have the both conformations, you can compare the carbon